One of our main goals in this class is concerned with the study of chemical reactions, specifically with predictions of the effect of pressure and temperature on their spontaneity. We are also interested in understanding the parameters that control the relative amounts of reactants and products when this reaction has reached equilibrium. So far, we have dealt with criteria for spontaneity and equilibrium for processes taking place at constant temperature and pressure. However, for the case of chemical reactions, we have been limited to the discussions of chemical reactions under standard conditions. Such conditions are often unrealistic since they assume that reactant and products are present in molar quantity in pure form under a pressure of 1 bar. Obviously, the reaction medium consists of a mixture of reactants and products, sometimes the existence of multiple phases, solid, liquid, and vapor, where each phase may contain multiple components. Hence, to fully understand the process associated with a chemical reaction, one needs to consider how the mixing of reactants and products and the changing composition of the reactive mixture impact the spontaneity of that reaction. To proceed toward useful predictions, we will need to determine the Gibbs energy of the reactive mixture using the chemical potentials of reactants and products, and understand how the Gibbs energy of the reactive mixture changes with the extent of reaction. From what we've learned in Chapter 3, we infer that when the Gibbs energy decreases, that is when delta G is negative, the reaction proceeds in the forward direction. If G has reached a minimum, then the reactive mixture has reached equilibrium, and unless the experimental conditions are changed, the composition of this mixture remains stable. If we find that a further increase in the extent of reaction would lead to an increase in G, then the reaction is no longer proceeding spontaneously in the forward direction, and the reverse reaction should occur spontaneously. Relating the reaction Gibbs energy change to the reaction composition will allow us to think about whether we can learn anything about spontaneity from the value of the standard reaction Gibbs energy change. It will also allow us to define a standard state that is much more useful in our work in the life sciences. We start today's lecture with a brief review of what we've learned so far this semester and how it will help us understand the actual chemical reaction process and the meaning of chemical equilibrium. Through a number of examples, we learned to relate the evolution of the Gibbs energy for the reactive mixture during a chemical reaction to the reaction Gibbs energy change, delta Rg, and explore the concept of reaction equilibrium in the context of the Gibbs energy of the reactive mixture. We then use reactants and products chemical potentials to calculate the reactive mixture Gibbs energy and to relate delta Rg to delta Rg standard and the reaction quotient Q. The relationship between delta Rg standard, and Q will be used specifically first to examine the spontaneity of chemical reactions at different stages of the reaction process. Second, we use this equation to discuss the role of standard conditions in predicting spontaneity and equilibrium and introduce the biological standard state. At the end of Chapter 2, we extended the second law of thermodynamics for processes occurring at constant temperature and pressure, which led us to introduce a new thermodynamic function called the Gibbs energy. We said that a process remains spontaneous as long as the Gibbs energy decreases. That is, as long as delta G is negative for the process. However, until now, problems dealing with chemical reactions were approached using calculation of changes in standard reaction enthalpy, standard reaction entropy, and standard reaction Gibbs energy. While these quantities do provide information about chemical reactions, they provide incomplete information because they assume that reactants and products are present as pure substances. So, to provide a more realistic thermodynamic description of a reactive mixture where reactants and products are intimately mixed with each other, we must combine information about chemical reactions in the standard state with information about mixing. Fortunately, this happens to be what we just discussed at the end of chapter 3. To relate Gibbs energies for species in a mixture to these of pure species, we use relationships between their respective chemical potentials and the species' activity in the mixture. This formalism will also allow us to examine the spontaneity of that chemical reaction not only at 298.15 Kelvin and 1 bar, but at any temperature and pressure.